these pendulum collisions.
So you could look at this and you could say, why is this angle, not straight up and down? I mean, where it's supposed to be hitting, it should be straight up and down. And you're saying, what? How does that even make any sense? How could it be a forward angle when it's supposed to be hitting when it's, vertical with gravity is where it's supposed to be hitting? So even little things like that, you just automatically say, well, what the hell is that? Is the center of mass of these two objects truly lined up? I'm not sure of that either. So where they collide, is this the center of the mass? I don't think it is. These experiments do require some precision, and he just couldn't care less about anything like that. And again, he still can't think that, okay, I have some obligation to have a release system that doesn't have any variance in it. That is, that it's, independent of human mess-up ability.
So once again, I redid this experiment and trying to make sure that the angles are perfectly fine and that the center of masses are perfectly aligned. Here we can see a simulation of a one mass colliding into a three mass and how they should behave after collision. This is what conventional science predicts. Over here you can see that both my real physical experiment and the simulation are superimposed on each other, and you can see very well that both the simulation and the real marbles perfectly align with each other. The three mass is equally big as the simulation sphere, and the one mass marble is equally big as the simulation of the one mass. They all perfectly align. So now let's run the simulation and the real experiment. As we can see, the incoming velocity aligns perfectly with the one mass, and after collision both the one mass and the three mass perfectly still align with the simulation model. So which means that yes, they reflect with half of the initial velocity. This is what actually happens. Conventional science predicts really well. Both the physical real experiment and the predicted velocities after collision match perfectly.
So you're doing the experiment on a scale that can't show the results. So again, he's got these little tiny, Newton used 12-foot pendulums, 12 foot long, okay? He's using, 1 foot, 18 inches, so any kind of defect in the experiment is going to have a dramatic effect. Any little bit of off, in terms of the...
Nope, it's not 1 feet tall, it's a lot longer. Look at that. Wow. So the balls are almost touching the ground. So let's measure. Let's measure the length of the wire, of the string. So like this, right? And over here at the top we have what seems to be around 145 centimeters. So it's almost 5 feet tall. Look at
that. Are far from adequate evidence to defend such an elaborate, amazing claim that I can put momentum in like a car, and I can increase its momentum by just making it hit something. I can hit something bigger with a spring, elastically, and I can make more momentum go forward.
Nope, there is no free momentum. Once again, momentum is about the motion of your system as a whole, while kinetic energy is about internal forms of motion inside your system. So what is your system? Your system is the box that you draw around the objects that you want to analyze. So let's say this is a one mass and three mass. This is the box, this is your system, right? The one mass comes in with 10 meters per second. So the box, your system is moving to the right with 10 momentum. Then after collision, so this one, they both reflect with half the velocity, which means this one continues with 50 momentum and this one with 5 momentum. So we have 50 momentum going to the right in your system, while at the same time the one mass reflects back with 5 momentum in the opposite direction. What does this mean for your system as a whole? 15 to the right and at the same time 5 to the left. We're gonna have a net momentum of 10 to the right, which means that before collision the box was going 10 momentum to the right, and after collision the box is still moving with a net momentum of 10 momentum to the right. There is no free momentum. Momentum is conserved for the system as a whole.